Welcome back. I am Anshu and you are watching Bottleneck. This is the Agenti cookbook series where we learn and implement design patterns for AI applications using hands-on examples. In our previous video, we explored prompt chaining for step-by-step sequential workflows and routing for dynamic and choosing the right path. While both are powerful, many real-world tasks don't need to run sequentially. Instead, they can be divided into smaller pieces that runs at the same time. That's where parallel execution pattern comes in. Now, if you have missed on my previous videos, I will be sharing the link in the description. Alright, so what is parallel execution? It is the idea of running multiple tasks like LLM calls, tool usage, or even subagents simultaneously instead of waiting for one to finish before starting another. The key logic is simple: identify tasks that are independent of each other and execute them together. This approach can significantly reduce overall execution time, especially when working with external systems like APIs or databases where latency can slow things down. Now, by issuing multiple requests at once, you make your system faster, more efficient, and better suited for complex workflow. In short, parallel execution helps you move from step by step processing to smart concurrent execution. Now, how it works. The process begins with the user submitting a request, which acts as the starting point of the workflow. Okay. Now from there, the request is passed to the parallel function, which executes all the independent tasks. Since the tasks, task 1, task 2, and task 3 are independent, they can run in parallel, significantly improving speed and efficiency. Once all the tasks are completed, the results are combined and collected. Finally, the system produces a comprehensive output by aggregating all the parallel results. Okay. Now, why parallel execution? Parallel execution enables AI systems to run multiple tasks simultaneously instead of sequentially, significantly reducing overall execution time. Now, instead of adding up duration of each tasks, the total time is determined by the slowest task, making the system much faster. It also improves scalability by efficiently utilizing resources such as APIs, compute, and threads, especially when tasks are independent or use different models. This approach naturally fits real world scenarios like content generation, research, and multiple perspective analysis, where problems can be divided into smaller components. In addition, it promotes a clean and modular architecture, allowing each components to be independently developed, tested, and replaced. Parallel execution also enhances reliability by isolating failures and enabling partial results and easier retries, which improves user experience through faster and incremental outputs. It further supports advanced pattern like multi-agent systems and ensemble methods while optimizing costs by using smaller models and retries and rerunning only failed tasks. Okay, so let's do a side-by-side comparison for routing versus parallel execution. The execution for routing takes one specific path, which again becomes sequential. However, you can add as many routes as you want. It is more flexible than a sequential workflow. Whereas in parallel execution, it is adaptive. The speed is sequential, depends on the total task or the time taken by the total task in together, and whereas the parallel execution, the time or the speed depends on the slowest task. The output is a single for routing because we get a single output. Here we have diversity, we have a composite output. Flexibility is low with routing and it is high with parallel execution. It is more fault tolerant when it is parallel execution. Scalability is moderate with routing, but it is more than the sequential execution, and it is very high with parallel execution. Similarly, for ambiguous inputs, the parallel routing is weak because it may not be able to redirect to the correct route if it is not able to predict what category it belongs to. Whereas in parallel execution, there is always a alternative or a default route where it can fall upon, and it is stronger for ambiguous input. Similarly, for extensibility, it is harder for routing, and it is easier for parallel execution. Now, let's take a look when to use parallel execution. Parallel execution is most effective when tasks are independent, okay, and can operate without relying on each other's output. It is particularly useful when faster response time is important as concurrent execution and reduces latency. This pattern works well for generating multiple outputs at once, such as different parts of content like subject line, email bodies, and CTA, that is call to action. We will see this as an example in the next video. Alright. It is also highly beneficial when interacting with external systems like APIs or databases, where handling multiple requests concurrently improves overall efficiency. Parallel execution is ideal for problems that can be divided down into smaller components and is well suited for building scalable systems. Additionally, it is a good choice when partial results are acceptable, when leveraging multi-agent or ensemble approaches, and when different tasks require specialized models, prompts, or configuration. Alright, and that brings us to the end of our discussion on the parallel execution pattern in Agentic AI. We have seen how breaking tasks into independent units and running them concurrently can significantly improve both speed and efficiency in intelligent systems. Up next, we will move from the concept to a hands-on implementation where we will see how to design and build a parallel workflow step by step. So don't miss it. Alright, if you enjoyed this video, feel free to like, share and subscribe for more practical insights into AI architecture and design patterns. Thanks for tuning in, and I will catch you in the next video. Thank you.